Hello guys, welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easier to understand. Today we're going to be looking at a problem that involves not only a turbine, but also a jet condenser over here. So in addition to the one process of the turbine, we're also going to have the process happening in the jet condenser. So the idea here is I'm going to, as usual, apply our thermodynamic ideas on each of the states, and we're going to see how things are changing from one state to the other to be able to grab enough data from a state so that we can completely define it. And once we have it defined, then things are easier to find. So let's have a look at the problem statement. Steam at a pressure and temperature of 1 megapascals and 200 degrees Celsius enters a turbine, where it is expanded adiabatically to a pressure of 10 kilopascals. The steam enters an isolated jet condenser, where it mixes with and is condensed by a jet of water at a temperature of 20 degrees Celsius and a mass flow rate of 5 kilograms per second. The water leaves the condenser at a temperature of 45 degrees Celsius. For a power output from the turbine of 150 kilowatts, calculate the steam consumption in kilograms per second, the enthalpy at the exit of the turbine, and the quality at the exit of the turbine. So I've written the information given here on each of the states, and I'm going to go ahead and call this one here state number 1. After the turbine, this will be my state number 2. The water coming in on the jet condenser is going to be my state number 3, and the flow out after the jet condenser will be my state number 4. Okay, so we know two things, two different properties at state 1, so that's completely defined. We're good to go on that one. Okay, after the turbine, we only know one thing about the exit of the turbine, so we only know the pressure. At the entrance of the jet condenser, we know the mass flow rate that's coming in and the temperature, so only one thermodynamic property of this guy. And on the output of the jet condenser as well, only one thermodynamic property. We also know that the turbine itself is being able to output work at a rate of 150 kilowatts or 150 kilojoules per second. So what are we going to do here? We're going to try to define, as usual, we're going to try to define these states, all of them. And to do that, I'll be applying energy balance, mass balance, continuity equation, and the things we've been talking about in the past few weeks. So note that the problem is framed in a way that there's no heat being lost. Okay, so that's to simplify our calculations and the process that we're going to use to be able to solve this. So let's start by doing a little energy balance and a little mass balance at the turbine. So I'm going to take this guy here as my control volume. Okay, I'm going to redraw it down here as I did. And let's think about the things that are going into my turbine and leaving my turbine. In terms of energy, I have entering my turbine, I have enthalpy from state 1, right? I have leaving, again, in terms of energy, the work, which is given in energy rate, right? And we also have state 2 as an energy leaving my turbine. Mass-wise, we have the mass flow rate from 1, right? Mass flow rate 1 here. And leaving, we only have mass flow rate for 2 because there's no mass leaving with the energy work output, right? So we have mass flow rate for 2 over here. So if I do a little energy balance, and this is my control volume right here, okay, there's no water accumulating inside my turbine. What does that mean? Well, it means that the mass flow rate 1 entering, minus the mass flow rate 2 equals 0, right? So what is that saying? Well, it's saying that's a steady state, and delta mass flow rate is 0. So in other words, what we're saying is the mass flow rate 1 has to be equal to mass flow rate 2. Okay, so there's no mass accumulating inside the turbine or decreasing over time inside the turbine. Okay, all the mass that's entering eventually leaves the turbine. We also can do an energy balance, right? And energy balance is going to tell us that the energy has to be 0, change in energy has to be 0. And then entering, we have H1, and then leaving, we have H2, and work output. Okay. Always remembering that this work output, we have it as a rate. So if I want to put it as a rate, I'm going to have to do rate for enthalpies as well, right? So if I want to rewrite that according to what we have in terms of data, then I would rewrite this as the difference from H1 times mass flow rate 1, which gives me a rate, minus mass flow rate 2, H2, minus the rate of output at work has to be 0. And I can write that finally as, okay, so that means that H1 minus H2 has to be equal to the 150 kilowatts divided by the mass flow rate of 1 or mass flow rate of 2, doesn't matter, whichever you choose because they're the same, right? Cool, so let's save this for later. I'm going to just leave this here as one of the equations that we have because we don't know much info, right? At this very instance, what we can do is we can get this enthalpy here because state 1 is completely defined, but there's no way we can find this and this at the same time. So that's one equation with two unknowns. All right, what's up next? Let's do a little energy balance at the jet condenser, which is the other process that is occurring here. So what do we have at the jet condenser? Well, in terms of energy and in terms of mass. So in terms of energy, I have my state 2 entering here, right? So enthalpy 2 entering here. I have the water mixture entering here, so that's my state 3 entering in terms of energy, and leaving I only have the state 4 enthalpy leaving. I don't have any other output from this jet condenser. In terms of mass, I have the mass flow rate 2 entering. From here, I have the mass flow rate of the water, that's my M3, and I have the output, which is mass flow rate 4. Okay, once again, same thing, mass balance, energy balance. Combine these things, we're going to see that, well, this guy plus this guy have to be equal to this guy, right? There's no mass accumulating here, so we can go ahead and just write it straight off. So the mass flow rate 4 has to be equal to mass flow rate 2 plus mass flow rate 3. And straight off the bat. Energy-wise, same thing, right? We have two things going in and one thing going out. So that means that the energy on 2 and 3 has to be equal to the energy on 4 because we can't create or destroy energy. So if there's no other energy leaving the system, then this holds true. And once again, I can put this in terms of, instead of having this in terms of energy, I can put this in terms of energy rate. So to do that, I can rewrite this as, okay, so this is the mass flow rate 2 times my lowercase enthalpy times mass flow rate 3 times my lowercase enthalpy has to be equal to mass rate or lowercase enthalpy. And I can relate this idea here. So I can rewrite this once again, divide everything by the mass flow rate 2, and I'm going to have this as my lowercase h2 has to be equal to 5 times h4 divided by mass flow rate 2 plus h4 minus 5 times h3 divided by my mass flow rate 2. Okay, why is it, where does this number come from? Well, it's 5 kilograms per second coming through, so this is my mass flow rate 3, right? So we knew that from the start. So where I had mass flow rate 3, I've subbed in 5. All right, remembering that I subbed this guy in by mass flow rate 2 plus 5. Cool. So I can, well, what do we have? I have 5 mass flow rate 2 multiplying on both terms here, so I can rewrite this once again, probably in a better way, which is 5 divided by mass flow rate 2 equals enthalpy 4 minus enthalpy 3 plus enthalpy 4. Okay, so this gives me a second equation with the same two unknowns as we had before, right? So note that we have the same two unknowns as before. I'm relating enthalpy 2 to my mass flow rate 2. Okay, so now we have two equations and two unknowns, right? We have the yellow equation up here, which relates enthalpy 2 mass flow rate 2, and here, same thing, enthalpy 2 mass flow rate 2. So as long as I can find the enthalpies for state 3, 4, and 1, I can solve this problem, okay? And with the information that we have from the problem statement, we can solve it. So let's go one by one and have a look at the enthalpies that we're looking for. So on state 1, we have 2 bits of information on state 1. We have the 1 megapascals and 200 Celsius, right? So that's straightforward. We have 200 Celsius. We're looking at this one here. And we're also looking at the 1 megapascal, so 10 bar, right? Same thing. So we're interested in these properties here for state 1. And enthalpy, which is the one we're chasing, is 28, 29. Cool. So that is my state 1. What about my state 3? That's the water coming in, right? The water coming in. We know the water is coming in at 20 degrees Celsius. And that's what the problem says, right? We have water mixing up at 20 degrees Celsius. If we have water mixing up, there's no mixture or nothing like that, then that means we can approximate the properties of water at 20 Celsius for the HF, right? Fluid. So let's look at the third state. That's the water. I have liquid water at 20 Celsius. 20 Celsius. Okay, so all I need to do is find, I'm looking at the temperature table, find 20 Celsius here, boom, here, and I want to find my HF, this guy here, so this color. So right here, so this is H3 is approximately equal to HF, which is 83.9. Brilliant. What else? State 4. What's state 4? It's the output, right? And what do we know about the output? Well, we know it's a mixture because it has the incoming from the turbine, which we don't know much about, and it has the water. And we know the temperature is 45 Celsius, right? So let's have a look here. Saturated water, temperature table, and I want 45 Celsius, which is going to fall between these two fellas here, between 44 and 45. Okay. Note that the problem statement says, let's go back to problem statement. Water leaves the condenser at a temperature of 45 Celsius. Okay, so we have a condenser, right? That's the idea of a jet condenser. We have a condenser that's taking in water, liquid water, and something that we don't know, but we can assume it's a mixture. We're going to be sure in a second, but we can assume it's a mixture. And it's condensing it, so it's outputting liquid at 45. Right? So what we have to do here is the same thing. We have to look at 45 Celsius and grab the HF, right? Which is the one for the liquid. So state 4 is going to be somewhere between 184 and 192. And all we need to do here is interpolate. So I have my temperature and I'll have my enthalpy, 44, 46, 184.2, 192.5. If you have trouble with this, there are videos teaching how to do this. You're welcome to grab them. But in this case, it's particularly easy because it's going to be the midpoint between these two guys here, right? You can just sum them, divide by 2 if you don't want to interpolate the old-fashioned way. So 188.35 is my HF, which is approximately equal to my H4. So I have all the enthalpies and now I just have two equations, two unknowns. So it's just algebra now, right? I just need to sub in the values that I have. I know that H1 minus H2 equals 150 kilowatts divided by this horrible 5 divided by mass flow rate 2, and I also know that H2 equals 5 over M2 times H4 minus H3 plus H4. And so I can sub in where I have H2, I can sub in this, and I can sub in the values as well. So I ended up with something like this: 2,829 minus 5 times 188.35, which is this guy here, divided by my mass flow rate 2 minus 188.35 plus, again, same thing, 5, and then 83.9 divided by M2, which has to be equal to 150 divided by M2. So if I multiply everything by M2, I can get it only on this term here and simplify my life. And skipping some steps, which I'm sure you guys can do on your own. I got this to be 0.25, 45, 77. It keeps going. So let's just approximate it to 55. That is kilograms per second. Okay, so that is one of the things we're looking for. Remember that this M1 equals M2 by the first analysis we did on the turbine. So it also equals approximately 255 kilograms per second. And the other thing that we wanted to do to determine is enthalpy 2, right? Which is part B of the problem. So part B is enthalpy with 2, which is quite simple now because obviously that's the other unknown on our two equation system. So I can just sub in where I had the equation that I had for H2. So H2 just 5 times divided by 2 the mass flow rate, 655, and then the enthalpy is 188.35 plus 188.35 minus 5 times 255, and this is 83.9. H2 is, what did I get? Approximately 2239.8 kilojoules per kilograms, which is answer for part B. And then part C finally asks us for the quality, right? So C is, what is the quality on state 2? And until this point, we weren't able to answer this question because we only knew one thing about state 2, which was the pressure, right? The pressure was 10 kilopascals. So only with that information, there's not enough for us to be able to determine the quality of it. But now we have a second piece of information, right? Second piece of information is precisely the enthalpy. So now we have two thermodynamic properties. We have the 10 kilopascals and enthalpy 2. So what I'm going to do is I'm going to look at the saturated water table. I'm going to be looking at the 10 kilopascals. So I'm going to be looking at 0.1 bar here. Let's do that. Down here. This is what I'm looking at. And I want to look at my enthalpy value. Let me grab it here, which is 2240 approximately, and see where it lies between the HF and HG, right? So let's look here. This is HF. So this is one for the liquid. This is the one for the saturated vapor, HG. And you know that this value here, H2, falls between the two, right? So it's smaller than this one, but it's greater than this one. So because it's between the two, so because HF is smaller than H2, which in turn is smaller than Hg, then we know this is a saturated mixture. And we can be sure of that. And not only that, but we can also calculate how much of each we have, right? How much of this guy we have and how much of this guy we have. And that's quite straightforward. Oops, the quality will be equal to the difference between what I have and the HF and the difference between the two, right? So I have 2239.8 minus 192 divided by, oops, come on, divided by the difference, and this is actually given, right? There's actually an entry for the difference there, so we don't have to do. So it's one less step for you to do on your calculator. And this gives me about 85.61%. Okay, so 85% of this guy here is vapor. The other 15% is liquid. Don't forget this is the output of the turbine, right? So remember that the turbine, let's go back. Where's our drawing? Here it is. Okay, so don't forget that steam is entering with a high pressure and a high temperature, highest temperature, okay? And it's leaving with a smaller pressure because we're actually outputting some work out of it, right? And if you look at the table we were just before, we had the 0.1 bar, but we also have 45.8 Celsius, which we know it has to be the temperature, the output temperature, right? So 45.8 Celsius. So it's going from 200 to 45.8, from 1 megapascals to 10 kilopascals. And in exchange, let's put it that way, in exchange, it's outputting this work for us here. And it's going from 100% steam, okay, 100% steam, which we were looking on the first table in defined state 1. We're looking at the superheated table. Okay, so superheated steam into a mixture of 85% vapor and 15% liquid. Okay, so those are the conclusions from this problem. Hope this was useful. If it was, make sure to subscribe. There's plenty more videos where this one came from. If you have any questions, let me know, and see you soon.